I don't have any 6033 in the news today. But today we're gonna start talking about making failures easier to handle, I guess is the way I'm gonna say this. So this is the slide that I left you off with at the end of the last lecture. All right, and so in the last lecture, we talked about we're starting to deal with failures, and we really dealt with disk failures in the last lecture. One of the reasons we're focusing on the disk is because it's the irreplaceable part of these systems, right? If the disk fails, the data is gone, right? And so in lecture, we talked about RAID, which is this system that, I have on the slide here, lets us recover from single disk failures on a machine. That's what we got up to with RAID 5. You can extend those ideas though. So for instance, RAID 6 lets you deal with 2 disk failures at once, and you could even extend these ideas a little bit further. In this model though, in lecture, we were really thinking about a single machine that is accessing all of these disks, right? So the disks could fail, but the machine would still be up. In recitation on Thursday, you saw GFS, which kind of on the surface maybe seemed like just a totally different system. But really, GFS and RAID are thinking about the same problem, right? Something fails and data is no longer accessible, right? GFS is thinking more about machine failure. So it's replicating data across machines, right? Which is something that we're also going to get to in lecture. The reason you're able to talk about it now in the context of GFS is because GFS works by having this more simplified model of what type of data it's storing and how that data is being used. So for instance, GFS is assuming that files, they're largely append only. The workload, once a file is fully written, it's typically read only, right? And that works fine. That works fine for GFS. It matches the type of data Google is storing on it and how that data is accessed, right? Notice that in both of those systems, other parts of the systems, the failure is sort of masked from them, or certainly from users, right? If you're using a machine that's hooked up to a RAID array, so to a set of disks using RAID, if one of them failed, if a sector failed or a full disk failed, you're still gonna be accessing your data just fine, right? You won't even necessarily know. You can build systems on top of GFS. And so when a machine in GFS fails, that system above it doesn't have to worry about that at all. You, in fact, can think about that really concretely because tomorrow at recitation, you'll talk about MapReduce, which is a system built on top of GFS, right? So MapReduce deals with certain types of failures, but it doesn't have to deal with other types of failures because GFS is there, all right? So where are we headed in lecture? All right, today in lecture, we're gonna start talking about, well, what does happen when an entire machine fails, right? What are we gonna do? We're gonna wanna be able to reason about what happens due to that failure. And then like, in some sense, write software that based on that reasoning deals with it, right? And this sounds difficult to do in the context of lecture. And it is a little bit difficult to do. We're going to try not to rely on any particular assumptions. So we're not going to rely on data being accessed in a particular way or files being read-only or anything like that, right? But if you imagine a system that's like thousands of lines of code, your machine could crash at any point, right? In between any pair of lines, during a line, right? How are we going to reason about all of those possible crashes, right? So to get a handle on this problem, what we're going to start doing in lecture is we're going to develop and we're going to implement a set of abstractions that make it easier to read about failures. So we're going to spend most of today talking about one abstraction, right? So this abstraction is atomicity, right? So an atomic action either happens entirely or not at all. So our goal in lecture is going to make certain actions be atomic, right? To adjust code so that these, no matter where a crash occurs, it appears to the system as though, well, either the operations didn't happen or it happened completely, like once the machine comes back online, all right? So it's going to appear to the user, it's going to appear to the rest of the system that the entire action happened completely or it didn't happen at all. All right, and we're going to go through a really like explicit example, but let's think about like what this is going to give us, right? Say you have an action, like some action your system is taking, it takes n steps, all right? System can fail at any point, right? Between steps 1 and 2, between steps 2 and 3, between steps 3 and 4, etc. All right. If we can guarantee that this action is atomic, it says that, okay, once the system recovers, either none of those steps were completed or they were all completed. You don't have to worry about like, well, okay, what if the first two completed but not the rest, right? Anything like that, right? And you're gonna see here, atomicity it's realistic, like from an applications perspective. It makes sense for the types of applications that we use these systems for, right? So let's see an example. So this is, it's kind of like a canonical example in this area. Canonical both because it illustrates the points really well, and it's something that probably the majority of you have experience with. All right, we're gonna transfer money in a bank, right? And for this lecture, we're just gonna assume there's like, we're not worried about concurrency. There's not multiple users here. There's just one user trying to transfer money from bank account A to bank account B. All right. So the way this is this is a pretty simple bank at this stage. Right. So I've got my bank account information stored in this dictionary. I'm subtracting amount dollars from account A and I'm adding amount dollars from account B. That's what a bank transfer amounts to in this lecture. All right. So the system could crash. All right. And let me illustrate a particular crash for you. Suppose it crashes here, after line 1, but before line 2, right? What has happened? Okay, we took amount dollars out of account A. Let's say it's $100, right? So we took $100 out of account A, but it was never added to account B, right? This is not what we want, right? You know, what should have happened, right? This problem is stemming from the fact that this crash is exposing some internal state of the action, right? The point between subtracting money from account B or account A and adding it to account B. What we really want is for this action to be atomic. Either no money moves anywhere, or it gets moved out of account A and into account B, right? And notice that, you know, the reason that we can talk about that is because we understand what this application is trying to do. We understand the nature of a bank transfer in the real world, right? We as humans are the people who say, oh, this is an internal state. This is an inconsistent internal state if I've subtracted $100 out of one account but not transferred it to the other, right? We as people know that. That's how we think about this. All right. So our goal for lecture, and we are going to spend like a good chunk of lecture on this. We are going to make this code atomic, right? We are going to ensure that the system completes both steps of this transfer or neither of them, right? No matter where a crash happens, right? So how are we going to do this? Okay, so this is our quest. I'm going to keep our quest down here at the bottom. It's going to get updated a little bit as we have some different ideas. We're going to go through a couple of things that aren't going to work. We are going to have a solution by the end of this lecture, but I will just tell you that the solution is not without problems, okay? So this is not like the final word on atomicity. It's a word on atomicity, okay? So here is my first idea, and I think that this first idea will illustrate some things for you when you're thinking of like, wow, what does this even mean? Like, what does atomicity mean? I don't get it. I don't get how a system could guarantee this. Okay, so let me give you one idea. Here's my first idea. All right, instead of keeping all of this bank information in memory in a dictionary, which is, you know, was an odd choice, I'm gonna have this file. Right, so some file, it stores the information about my bank accounts. It doesn't matter how the file is set up. It's just a file. It's got the data in it. I'm going to read in that file, gives me my dictionary. I'm going to do this transfer in memory, and then I'm going to write back to the file. All right, so let's see why this is an idea worth pursuing. It's not going to work the whole way, but think about the crash we had before. Right, my transfer code has read in that bank file. In memory, it subtracted whatever amount of money from account A, and then it failed. When the system comes back up, did this transfer happen? Are there any lingering effects of this transfer? What do you think? You can put it in the chat. You can even send it just to me. If you don't want public, you can do like thumbs up. Thumbs down for nothing happened. What do you all think? You can even say words. That would be a wild notion. All right, if we crash here, did the transfer occur when this machine recovers?
No, because we were only changing a local copy.
Exactly. Yeah, I changed this copy in memory. Machine crashed. I didn't change anything about the file, right? When my transfer code gets run again, the only thing my bank here can do, it can only transfer money. It's a limited bank, admittedly. All right, we're going to read from the bank file. Nothing changed in the bank file. Nothing happened. All right, this is what we mean when we say that, okay, a crash occurred, but after recovery, it appears as though nothing happened. Like, yeah, we can look at this code. We know that, okay, the first line actually executed, but there were no permanent effects of that execution, right? So nothing happened, right? Initial problem solved. Second problem, suppose we don't crash there. Suppose we crash while writing the file, right? Well, this is probably not great. You can certainly imagine that this leaves bank file in some sort of weird intermediate state. Maybe it's like halfway written. It just, any number of things could go wrong there, right? In some ways, this has violated what you might consider like the golden rule of atomicity, which is never modify the only copy, right? We effectively just had one copy of this bank file. We're going to try to change it. The machine crashes while we're trying to change it. That's problematic. All right. But this idea of actually storing the data in a file, we can stick with this. All right. So I'm going to update this code a little bit for you. Same general approach, but we're going to read in our bank file. Right. This time, we'll make our changes in memory, and then we'll write them out to this temporary file. Right. And then we're going to rename. Right. So that temporary file now it becomes the bank file. All right, so what could go wrong here? All right, a crash in the middle of the transfer, right? When we subtracted amount from account A, but before we've added it to account B, that's still okay. All right, now, what about the analog to our previous crash? Right, what if we crash while we're writing to this temporary file? Well, we crash while we're writing to the temp file. Maybe it gets written halfway. Maybe it gets written in some weird corrupted way, right? We don't know. Machine comes back online. The first thing the code does, it reads the original bank file. Nothing's reading that temporary file, right? It is as if this transfer didn't happen, all right? So this becomes better. Now, you might look at this code though and say, have I not just like pushed the problem further, right? You should be able to anticipate the next crash I'm going to ask you about. What if we crash while we're renaming the file, right? This could potentially be bad, right? I've written all of my data to this temporary file, right? I'm taking my original bank file, trying to get to point to that data, but something fails. Something fails in the rename, right? And so we would have a question like, well, is the bank file, is it pointing to the old data? Is it pointing to the new data? Is it pointing to nowhere, right? This would be problematic, right? And in some sense, I have just moved the problem. Here's what we're going to do. We're going to make rename itself into an atomic action, right? What that guarantees, if we can do this, and we're going to be able to do this, if we can do this, this says that, okay, well, the rename either doesn't happen, all right? And if it doesn't happen, the transfer didn't go through, or it happens completely, right? In which case the transfer did go through. Because there is a point in this code, right? So this line, this rename, this is what we call the commit point, right? A crash before the commit point gives old values. It says, okay, this action did not happen. It did not commit, right? No bank transfer occurred, right? Any crash here and above, no transfer occurs, right? At the same time, any crash after this, there's no code after this, but any crash after that, the transfer happened, right? That rename is my commit point, right? The commit point has to be atomic, right? That otherwise you don't have atomicity. So You could ask yourselves, well, why are we going to try to make rename atomic? Why didn't we just try to make write accounts atomic, right? That is a very good question at this stage, right? The quick answer is that it would have been impossible, but I'm going to point out to you why exactly we couldn't have made write accounts atomic and why we're going to be able to make rename atomic. A quick answer is because rename is a much smaller operation. All right, so we have to kind of zoom in a little bit. We're going to make rename atomic, which means we need to think about, well, what does it actually mean to rename a file? So we're going to have to kind of drill down into this code, right? So to do this, I'm going to move the bank transfer account. It's over here. It's in gray. You don't really need to reference it during the next couple of slides. I just want you to remember that it's there. All right. The goal here is to transfer some amount of money from account A to account B. All right. And we're zooming in on this line rename. The reason we're zooming in is because we want to believe that it's atomic. And there's no reason that we should believe this yet. Benjamin, in the chat, right? You're not seeing how we can guarantee atomicity. You shouldn't see it at this point. You should be super skeptical. You should be like, there's no way, right? I could crash in any, like, in machine code, right? It's going to be wild, but get ready, all right? So let's think about renaming. What does it mean to rename a file, right? What is going on there, all right? To talk about this, we're going to need to talk about some relevant data structures. So we're thinking of renaming a file in Unix. You all love Unix. Here it is again for you. All right, we're going to deal with these two files, right? Bank file and temp file. There are directory entries for both of them, right? We're going to care about the inodes that they point to. All right, so I'm making up numbers here, inodes 1 and 2. All right, we're going to care about that. And then just to illustrate a little bit about what's stored in these inodes. Right, so there is the actual data that constitutes the file, right? And then there's some reference counts, right? These are the relevant data structures for this example. So what needs to happen? What does rename do, right? In this example, there's really only 3 things happening. I've got to take my original file, bank file, have it point to the new data, right? So it's going to have to point to the second inode instead of the first. Then I want to delete all of the references to temp file. I want to delete its directory entry. I want to delete the ref count on the old data, right? So super, super, super important. You may never have thought about renaming a file before, and that's totally fine. Super important is to understand renaming a file does not, we do not have to move large amounts of data around our system, right? If file pointed over here, now it needs to point over here, right? It's a relatively small operation in the grand scheme of things, right? So let's look at the code. Nothing's going to crash yet. We're just renaming a file, right? To make all this work, we need to know what inodes we're dealing with. Unix gives us a lookup function. We're not going to need to worry about the internals of the lookup function, but we'll be able to get the inodes associated with both of these files, right? Step 1, point that original file, which is bank file here, right? Point it to the new data. Point it to the data that represents that's in that temp file, right? That's just this, right? Set the directory entry equal to this new inode. And you can see up on the top, I'm also making the changes. So you can see the changes happening, right? Then, okay, removing the temporary files directory entry, that goes away. Decrementing the ref count on the old data, that goes down to 0. Garbage collection will come along for us at some point and clean that up. All right. This is what it means to rename a function, to rename a file, right? So we have to guarantee that this is atomic, which means we have to start thinking about, like, well, what if things crash? All right, let's do it. Suppose we have a crash here, or really anywhere above this, right? We've looked up the 2 inodes, but we haven't changed anything about the directory entries. We haven't changed anything about ref counts. Rename didn't happen. We didn't actually rename this file. We just looked up some metadata. All right, the system crashed here. It came back online. The rename didn't happen. The bank transfer didn't happen. Okay, that's crash 1, right? So it's as if rename didn't happen, right? Oh, that line got messed up on the iPad. this arrow, I'll fix it for you on the slide, should be right here, right in between the two lines. So imagine a crash is there, right? After we've set the directory entry to equal this temp inode, right? But we crashed somewhere after it, right? Before we removed the temp file from the directory entry, or maybe after we removed it, but we didn't decrement the ref counts. Well, this is kind of an interesting case. The rename here happened, right? Bank file points to the new data, right? You can see that up here. Bank file is pointing to the right place, but there's some bookkeeping that is incorrect. Ref counts are wrong. Temp file is still there, and we probably want to clean that up, right? But sort of, modulo that, which we're going to deal with, it looks like the rename happened here, right? Which means this gives us some indication that this line, right, this line right here might be the actual commit point of this function, right? Which means we need to guarantee that this line itself is atomic. So like we started a bank transfer, then we zoomed into rename. Now we're zooming into this single line, which we know is more than one line in assembly, right? The single line where we're setting a directory entry equal to something else. I am upset that my arrows got messed up, right? So again, this crash is right here. A crash during this line seems really bad, right? It would be really problematic to crash during this line because what does the bank file point to now, right? Did it get updated correctly? Did it not? All right. Here is, in some sense, the thing that our entire system rests on, right? Nothing in this lecture is possible without the following fact, which is that single sector writes on a disk are atomic, right? Which is kind of wild. That seems, how could that be, right? Remember first that a single sector in a disk is a very small amount of data, especially if you're thinking of a magnetic disk, a spinning disk. Most of the time is spent spinning, right? Doing the write is very, very small. Most disks save enough energy to complete a single sector write, even if they crash mid that write, right? The time spent writing a sector is small. There is a small capacitor that suffices to power the disk for a few microseconds. And that capacitor is there to finish the write, even when there is a power failure. If the write didn't actually get started, like if the disk was still spinning and we didn't get to the sector, then there's no need to complete it, right? That action is still atomic, right? Which again, this should be giving you fond memories to when we talked about operating systems. Yes, Derek, this constitutes dedicated hardware bootstrapping to a higher level property. You cannot make this work, right? If you don't have this very relatively small guarantee from your hardware. But it's kind of amazing, right? The hardware is guaranteeing this very, very small amount of atomicity. A single sector of data is so small. And we're going to build this huge system on top of that guarantee. All right. So even though, yes, of course the code can crash in the middle of that line, right? Systems can crash anywhere, but that write is either going to happen entirely or not at all. All right. So at this point in the lecture, we are almost exactly halfway through lecture. It is 2:29, right? This lecture goes pretty deep. Okay. So we're going to take 10 to 20 seconds. We're just going to look at this calm pool. Okay, y'all can turn your cameras off. I will turn my camera off, all right? Do some breathing for 10 seconds, and then we'll come back. Okay, we're going to keep going now, right? That's a nice break, right? Sometimes you need 10 seconds just to breathe. All right, that's always okay. You can always take 10 seconds just to breathe. And I think, again, we had to zoom in so far down. It's important to just gain some perspective. There are nice pools of water out there. It's good. Okay, so now I left you with this. And again, my iPad has failed me. This arrow should go here because this is unsatisfying, right? This looks a little bit messy. We said, okay, well, after that commit point, the rename did happen, right? Like morally, the rename has happened. Bank file points to the new data, but there is all of this bookkeeping, right? That's wrong. So let's try to fix that because we don't want those things to be wrong. We don't want temp file around anymore. We don't want the ref counts to the old data to be wrong. It won't get garbage collected, right? It's all this stuff. Okay, so one approach to solving this problem would be to try to be really, really careful about where we increment ref counts and where we decrement them. So we could try adjusting the code, right? So incref here is just increment ref count, decref is decrement ref count. You can analyze this code a little bit. You'll get to a point where like some things are cleaned up, but honestly, this is still incorrect. This is a mess. Rename should not have to be this complicated. All right. And here's the thing, rename doesn't have to be this complicated. We don't have to go through all of this effort to make sure everything is perfect, like before a crash. The reason is because we get to recover from failures. We can have a process that cleans things up, right? The disk has crashed. When the disk comes back online, it can check for all sorts of bookkeeping type things. It can update ref counts, right? It can find these temporary files and unlink them, right? Running this recovery process, even if we crash during the recovery process, it is okay. We would be able to run this particular style of recovery over and over and over with the same results. All right. And I really want to stress, sometimes I present this and I always have some students that are like, they want everything to be perfect before the crash. Like they want to know that like that temp file gets deleted when it needs to, that those ref counts get cleaned up. They can't, right? You can always crash between the actual rename of the file, right? Pointing to the right inode and doing something else. But you get to recover. You get to fix things when the machine comes back on. All right. So time for reflection, right? Having this process means we don't have to worry about so much, right? We clean up after the machine comes back online, right? So reflect. We're not done with lecture. There's 20 minutes left. Well, let's reflect on this process. This approach has a name, shadow copies. We have kind of a shadow copy of the data in this temporary file. Why did they work at all, right? We haven't generalized this approach. We've only looked at it in the context of a single bank transfer. But why does this work at all, right? The reason it works at all is because we perform, any updates / changes on a copy of the data, right? And then we atomically install that new copy, right? We're able to do that because we have this single atomic operation. We have this single sector rate, right? It requires a small amount of atomicity from a lower layer, but that is reasonable, right? Then this is the point where you can now think about, for instance, we were able to make rename atomic. Imagine if we had decided to make write accounts atomic, right? Write accounts is writing this entire file, right? Imagine that it constitutes every bank account in my system. That's not going to be a single sector rate, right? That's going to be many, many sectors. We wouldn't really have had a point at which we could, guarantee atomicity there. Yeah, we need a really big capacitor, right? That is the reason we didn't start down a path of trying to make write accounts atomic, right? But looking at this setup and saying like, okay, we can write data to this other place and then have a very small operation, which we can guarantee is atomic, to install that new data. That's an idea that's going to stick with us. All right. This is, in fact, kind of a general approach for atomic operations, right? Write a temporary copy of the data. So, like, have 2 copies of the data, atomically switch to the new copy, and then remove the old copy. All right. Now, let's think about where we might go with this, right? Because if this is going to be a useful concept to us, we would want to make sure that it works in more than just a bank transfer, right? And for right now, let's worry about correctness, right? Let's not worry about performance. There are some glaring performance issues with this code, and we will come to those. Let's think about correctness. You know, this seems to be working pretty well, where there's just a single writer with a single file, right? We haven't talked about concurrency yet, right? We haven't talked about multiple files or directories or anything like that. And you know, those things are tricky. It's tricky to imagine how to take shadow copies and generalize them to multiple files or to directories, and just it's maybe not impossible, but it's a lot to deal with. And it's hard to think about, you know, if I have multiple users that might need to be accessing this data, what would I want to happen? All right. So because we're sort of starting to think about concurrency, let's go ahead and make this idea a little bit more precise. We're not going to solve concurrency today. In fact, we're not going to solve it until next week. All right. But I've had this top abstraction up here for you at the top this entire time, atomicity. Let me give you the second abstraction that's going to make life better. Right. The second abstraction we're dealing with is isolation. Right. Isolation refers to how the effects of a particular action are visible to the rest of the system, right? Like one very concrete example would be to say like, okay, when one process writes a piece of data, when is that write visible to all of the other processes? There are a lot of different levels of isolation. There are sort of like lots of types of isolation that you could get. We're going to define them more precisely as we encounter them. But in the lecture, we're going to go for a particularly strict type of thing. Where we're going to say, okay, if I have 2 actions that are run concurrently, right, it should appear as if they ran serially. Either A1 ran entirely before A2, or A2 ran entirely before A1. So this kind of before and after notion, right? So let's think about this in terms of the bank transfer code, because you might think of this. You might have heard me say the word concurrency and said, oh yes, I was hoping we could do more with locks, because we all had a lot of fun with locks at the beginning of this class. We did have fun with locks, right? Can't we just put locks here? Right? This is kind of working for one user, one file. Let's try to allow some more users, right? But just lock the whole thing. All right. And this is the approach, right? This is the approach that I told you all to use at the beginning of O33, right? Start with coarse grain locks and then refine them. But you all can look at this code. You know this is going to perform poorly. Right. This means only one piece of code can be in here, or one process can be in here at a time. If I'm trying to transfer money from Karen's account to Howie's account, and also from Wesley's account to Rachel's account, I have to do those one after the other. That doesn't make any sense. These are 4 different people, 4 different accounts. Our bank is going to perform terribly if everything has to actually run in serial. But you also saw us kind of, you know, in many ways come down hard on locks at the beginning of O33. We need them, but they're tricky. We saw examples where, you know, we needed global reasoning. That's really messy, right? Even if you look at this code, right, I've got a lock, you know, inside of my transfer code. It doesn't say anything about, you know, what if I want to make higher level operations proceed as one action, if I want to do 3 bank transfers as one like atomic thing, right? All right, so we're going to come back to this. We are going to see locks again, but we're going to incorporate them in a particularly systematic way to get isolation. And the reason I bring it up here is because I want you all to start to get used to both of these abstractions. And whenever we say concurrency, people are like immediately, oh, locks. It's going to be a little bit more involved than that. All right, so now you know about both of these abstractions, atomicity and isolation. It's time for you to get some more vocabulary, all right? So atomicity and isolation, and then I say here, and thus transactions make it easier to reason about failure. So transactions are the umbrella under which atomicity and isolation are going to sit for us. So here are two transactions, right? This is how we are going to start talking about our systems operating. They're going to be transactional nature. So you can see some transaction syntax here. We're not going to be super picky about transaction syntax. They have a clear beginning and an end, right? And when you're working with transactions, right, what this says is that, okay, everything in between this begin and end, it's atomic, right? The underlying system, which is what we are going to build in lecture, the underlying system guarantees that all of those steps, right, happen as an atomic action, right? Same thing for transaction 2, right? Everything in between that beginning and end happen as an atomic action. And then for us in lecture, we're also going to say, okay, we want to run these transactions, concurrently as much as possible. But in terms of the effects, in terms of what rates we see when, things like that, right? It's going to have the same outcome as if I had run, T1 first and then T2, or vice versa, right? So in lecture, we're building all of the stuff that goes on underneath, right? All of the stuff that allows transactions to be atomic and to have the type of isolation that we want. And now you have the language to talk about buying llamas more precisely, right? When you buy a llama on Katrina's Amazing Web Suite, we're going to want that action to be a transaction, right? Either your llama purchase goes all the way through, or you didn't buy a llama, right? That ultimately, we're getting to the point where you will be able to purchase a llama on Katrina's Amazing Web Suite, right? Just as an aside, at this point, since we've done a little bit of talking about locks, right? Locks ensure that some piece of code, only runs on a single thread at the same time, right? They are going to come up when we talk about isolation. They have nothing really to do with atomicity, right? If you have some code in between a lock and it crashes in the middle, it doesn't like gracefully roll back the code to before the action occurred, right? So locks, they're going to component isolation, but they have nothing to do with atomicity. All right, so where are you now? Where are you now in the world of failures? All right, this is where you were before. This is where you were when you came into this class today. Now you've built up into a different type of failure. Now we're imagining an entire machine fails. Realistically, we still got only one user. We still got only one machine. We're not replicating data across machines. We're just on this one machine, but the whole machine can fail. All right. And we've started talking about ways to make this easier to reason about, right? We don't want to have to reason in our systems, like in our code, and say like, okay, so there was a crash between line 1 and line 2. How do I handle that? A crash between line 2 and line 3. How do I handle that, etc. We want to give our systems the ability to use transactions, right? Because these are going to provide atomicity and isolation, right? It's going to make it easier for us to reason about failures, right? And I really want to stress, our job in lecture is to understand how our systems make those guarantees. How do we get something to be atomic? How do we guarantee isolation? Right? Our system is not, our goal in lecture is not going to be to like look at different pieces of software and decide what should be a transaction, right? It's to support the transactions. So how far have you come? Well, we solved our original goal for today. We completed our quest. Our quest was to make the bake transfer code atomic, and we did, right? We used these shadow copies. But, that's one user in one file, which is not going to be useful forever. However, the biggest problem that you have right now in that bank transfer code, every time I make the smallest change, I have to rewrite the entire file, right? Imagine, we start to run a global bank, which for some reason is still keeping all of its bank account information on one file. Every time there's any transfer, we have to rewrite the entire file. That is the reason we're not going to stick with shadow copies. All right, it says this performance problem, it's not going to work for us. However, the ideas behind shadow copies, those are going to carry over to what you're going to see in lecture on Wednesday. This idea of, kind of having two copies of data around, atomically installing updates, that's all sticking with you. So it's not like shadow copies were worthless endeavor, right? We're gonna pivot a little bit to something that is better in every way, right? Especially in performance, right? And where are you in isolation? We don't have that yet. We have some ideas about locks, but they're tricky. We don't have any sort of systematic way to apply locks yet, all right? But as we go through lectures, we will solve these problems, all right? Wednesday, we will get atomicity working for sort of, one machine, all right? Next week, we will get isolation working on, again, basically one machine. And then the week after that, we'll talk about like, okay, suppose I have a really big system and data is spread all around the system. And some of my transactions need like data from this machine and data from this machine, right? Maybe they need to do a write in both places, right? Now we've introduced a network into the equation, which always gives us problems, right? We're gonna solve that the week after next. But surprisingly to some of you, this is the end of lecture today. This is like a jam-packed lecture. There's so much code. I don't try to pack anything else in here. So I will hang out for questions. You get 8 extra minutes back into your day. My staff also gets 8 extra minutes. We don't have a staff meeting until 3, so just enjoy these 8 minutes, stick around, ask questions. I'll see you Wednesday.